Hello everyone, this is Aditya. Before starting this video, I want to clarify one thing that I am really not well and I was never in the condition to record this lecture, but to help you all, I am recording this lecture. So please bear with me because I might sound very much down or maybe very much less energetic than my other videos. So please bear with that, but still I tried my best to provide you the best content which I could give. So please do understand this problem and please bear with it. And now let's start with the video. And I want to apologize also because I could not make the video earlier because of my health. I really did not got time actually to make the video because I wasn't in the condition. Right now also I'm not in the condition to record this lecture. Still I am doing. I really apologize for being so much delayed, and I again say sorry because in the lecture I might sound really different again. So I am really sorry for the further video also, but I hope that you will really understand this lecture and you will do great. Hello everyone, this is Aditya, and today we are going to cover linear algebra in a one shot for engineering mathematics 2. But before that, please do like, subscribe my channel, and please support this video and please support my channel so that this video can reach to maximum number of people. And now let's start with the video. Okay. So first of all, we will see system of linear equations in linear algebra, right? And of course, I have made algebraic structures and ordinary differential equation one shots before, so you can check that out. And of course, now here coming to the topic. And I'm a bit unwell, so please bear with me, okay? So now let's start. So system of linear equation. Well, what do I mean by system of linear equation? Well, equations involving the variables with degree 1, right? Basically, that is it. So if I want to say, suppose 2x plus 3y is equal to 7 and 5x plus 2y is equal to 3. So this is the system of linear equation, right? Why? Because it involves the variables with degree 1, okay? So how do we write it in a general form? Like suppose you have m equations and there are n variables. Let's see. So this is the coefficient, it is a variable, and likewise this 1 n xn is equal to b1. What is the next coefficient? It was a11, so it will be a21, x1, a22, x2 till a2n xn is equal to b2, right? Is it correct? Okay. And it will go so on. And suppose there are m equations, which means it will be am1 x1 plus am2 x2 till amn xn is equal to bm, right? You can understand this, okay? So this is a linear equation, the system of linear equations involving m variables, I mean m equations and n variables, right? Okay. So how do we express it in a more compact form? Well, we use a matrix form to represent it. First of all, we will see with respect to this, then we will come to that, okay? So matrix form is given by ax is equal to b. Well, don't worry, what does it mean? I'm telling. So here A is the coefficient matrix, right? So how do we express this? Let's see. Okay. So you have the coefficients 2, 3, 5 and 2, right? So A in this case will be equal to, A is equal to 2, 5, 3 and 2, right? This is with respect to the variable x, the coefficients of x, and this is the coefficients of y multiplied by, I mean, of course not in this one. Now if you want to represent it in the form of ax is equal to b, what you will do is that you will write 2, 3, 5, 2 multiplied by what is x. X is just the set of variables which are given here, x and y. There are two variables, so write x and y is equal to 7, 3. And of course when you multiply it, what you will get, 2x plus 3y and 5x plus 2y is equal to 7, right? And this is of course the same equation, right? Just we represent it in a more compact way. Similarly, You can write a in this case as coefficients a11, a21 till am1, and this goes till a1n, and this will go till amn, right? So this is how you represent the coefficient matrix in a general way, and the variable is of course x1 till xn, and this is the coefficient with respect to x1, and this is still xn. Of course I did not wrote in the between, but you can understand it. Okay, so again ax is equal to b. What is b? B is equal to b1 b2 till bn, right? So basically you can write it like this, even a11 till am1 till and this one a1n, and this goes till amn, multiplied by x1 till xn is equal to b1 till bm, right? I were understanding that how am I getting this. Okay, so let me raise this, and then we will discuss further. So let's see that when we say the system of linear equation is consistent and when it is not consistent, I mean inconsistent. So for consistent, for being consistent, it must have at least one solution, right? And for inconsistent system, there will be no solution, right? Of course in this case it can be finite, I mean one solution also, and there can be infinite solution also depending on the conditions, right? So basically this is what I wanted to say, and now we will see further. So let's see that how do we solve linear equations, the system of linear equation. Well, there are many methods like Cramer's rule, the matrix rule, which you all know. So we will be sticking towards Gauss elimination method only, which is important also. Gauss elimination method, right? Okay. So let's see that what is it actually. Okay. So for this you must know about elementary row operations, right? What are those? Suppose you have a matrix, so in that case you can interchange the ith row, I mean ith and jth rows. It means ri can be replaced with rj, right? Like this. And multiplication of the ith row by a non-zero number, suppose lambda, right? You can do multiplication like this, right? Ri, it can be written as r, can be multiplied with this, right? Okay. And addition of lambda times the jth row to ith row. Well, don't worry that what am I saying all this. Of course we will see example, then you will understand it better. I'm just telling you theory right now. Okay, so don't worry about it. So it will be ri is replaced with ri plus suppose lambda times rj, right? This is how. So of course I've written everything. Now we will see the problem to understand the theory better, right? Okay, so give me a minute to raise this. So now we have a question to solve, and let's see how we are going to solve it using Gauss elimination. Well, you can write the coefficient matrix as 1 2 1, right? 1 3 2, right? You can see the coefficients over here, and 1 1 3, right? This is the coefficient matrix. Okay, and what is B matrix? It is 4 7 9. So to apply Gauss elimination method, you should know what is meant by augmented matrix. Well, let's see what is it. So suppose you have this matrix and this matrix and you want to augment them, I mean to club them together, right? So what we are going to do is that we are writing it like this, and it is 1 2 1 1 3 2 1 1 3, and you have clubbed this matrix over here 4 7 9, and this is called a augmented matrix, right? It's just a fancy name, but it's just this, nothing else. The clubbing or the combination of two matrices like this. You just clubbed it, like okay. So let's see how we are going to now solve. Well, now we are going to apply elementary operation methods for row, of course. Okay. So notice that this is your row 1, and this is your row 2, and this is your row 3, right? I hope this is understandable. It is simple. Okay. So let's see. Okay. So this is your augmented matrix. Write it like this. We get over here 1 2 1 1 3 2 1 1 3, and here get this. Okay. So okay, we are going to apply elementary operations, but how are we going to apply? Well, basically you have to create zeros. What do I mean by that? Suppose here it is 1, so beneath it you have to make all the numbers as 0 to solve the equation, and in this case you have to make a 0 over here to solve the equation. Well, let's see, then you will understand it better. Okay. So how we are going to create a 0 in the second row? Well, if you remember, we can do r2 as r2 minus 2 r1. Why? Because twice of r1, when subtracted from it, we will get a 0 over here, right? Let's see, 1 1 1, right? And this will become 0, and 3 minus 2, it will become 1, and negative 2, this will become negative 1. You get 1 2 3 and 4. 7 minus 8, it will become negative 1 and 9, right? Is it correct? So now what we are going to do is, we have got 1 0. Now we need to create a 0 over here also, so that there are all zeros beneath this number, right? So R3 we will change, I mean we'll apply the elementary operation R3 minus R1, right? Is it correct? Okay. So you get 1 1 1, and here 0 1 negative 1. When you subtract, you get 0 in this case, and you get 1 over here, and you get a 2 over here, and you get 4 negative 1 8, right? Okay, let me erase this. I'm sorry, it was a 5 over here because 9 minus 4 is 5. Sorry. Okay, so now you get 1 1 1 0 1 negative 1 0 1 2 augmented 4 negative 1 5, right? You get this thing. Now we can make another 0 over here if we subtract r3 from r2, right? Well, we can. So we get r3 as r3 minus r2, right? Simple, very simple. 1 1 1 0 1 negative 1 0 1, I mean 0 0, and then it will become 3 4 negative 1, and this will become 6. Okay, we got zeros over here, but what is its use? Well, it has a great use. Let me erase this and then I will explain. So if you remember that originally the matrix was like this, ax is equal to b, right? Remember this? Okay. So in this, the coefficients were, this was for x1, this was for x2, and this was for x3, right? Is it correct? Okay. So now we'll place the variables at the places where they are required. What I mean is that this one was for x1, this was for x2, this was for x3. So you write x1 plus x2 plus x3 is equal to 4. This is your equation number 1. And what you get is 0 times x2, I mean x1, plus 1 times x2 plus negative 1 times x3 is equal to negative 1, and 0 times x1 plus 0 times x2 plus 3 x3 is equal to 6. And now you know that why we were trying to make 0 in this row, because we can easily then find the value of the last variable in this case. We get x3 as 2, and now it is very simple. You can just substitute the value of x3, so you will get the value of x2 in this case, and then you will get the value of x1. I'm not solving that, it is very simple. So this is called, what is this matrix called? Well, it is called echelon form. Echelon form, right? Okay, did you understand that what is it actually? And when you are substituting the variables back to their places, it is called back substitution. This is back substitution, right? Okay, don't worry about the echelon form, we will see it in some more time in great detail, but for now understand that this is echelon form, and basically in this case you are going to get something called pivots, and using that you are going to understand more concepts. Okay, so don't worry about it, just wait. So this is how you solve it using the Gauss elimination method. So first it is to create augmented matrix, then you go to echelon form using the row operations, and then you use back substitution, right? Okay, so this is how the process is going to find the values of the variable using the Gauss elimination method. Okay, so let me erase this and then we will be right back. So this was the echelon form which we had got, and in this we are going to discuss about pivots. What is it? Okay, so this is your first variable, I mean the first number or first entry. So for this case, if this number is non-zero and is surrounded by zeros, I mean beneath it it has all zeros, and in the left it has zeros. Of course there's no number at the left, so we don't care about that. So we care about that if this number, it should be non-zero and has zeros beneath it, then it is called a pivot, right? Okay, is there any other pivot over here? Well, if you consider this one, it has a variable, I mean a number which is not zero placed beneath it, so of course it can't be, right? Okay, so can it be a pivot? Well, it is surrounded by a zero beneath it, right? And towards the left also, which means that this is also a pivot, right? And in this case it is surrounded by zeros towards the left, and of course there is no number in the beneath, which means that this is also a pivot. So in this equations there are three pivot, right? So number of pivot in this case is 3. Well, why am I telling this? Well, let's see. If number of pivots is equal to the number of unknowns, then we have unique solution, right? Do you understand this? If the number of pivots is equal to the number of unknowns, then we get a unique solution. Notice that here the number of pivots was 3 and the number of variables were also 3, which means that that is why we got independent, I mean unique solutions in this case, right? Not independent, sorry. Okay, so I hope you understand what is a pivot in a basic term, and of course we will see some questions to understand it better, right? Let me raise this, then we will be right back. So this is an augmented matrix, and now we are going to solve it using the Gauss elimination method, right? Okay, so let's see. Well, in this question I will leave the calculation part to be done by you only, but I can tell the operations that what you are going to do. Well, I won't tell that. Okay, you have to do it on your own. I can tell that what will the final matrix which you will get. Let me see, what is it after elementary row operation, you are going to get 1 0 0 1 1 0 0 negative 1 0, and in this case 4 negative 1 and then 6, right? Okay, so notice that in this case, when you substitute the variable over here in this row, you are going to get 0x1 plus 0x2 plus 0x3 is equal to 6, which means that 0 is equal to 6. Well, it is clearly a wrong statement, which means that this system was inconsistent, right? I mean, is inconsistent, okay? Is it fine? Because you won't get a solution because of this row, right? I hope you're understanding. You just substitute the variables over here, right? Okay. Well, there's one more thing over here. Suppose, just assume that if it was not 6, it was 0. Suppose it was 0. Then in that case, you would be getting over here 0, which means 0 is equal to 0, and it is clearly a valid statement. So in this case, you would get infinite solution. So you can just see that just by changing the variable towards 0, you got infinite solution, right? And this is how the things are going, right? Don't worry about it. I hope that you're understanding it and you're enjoying the video. And one more thing to be noted over here is that this is a pivot. Of course it is, since it is 0 beneath it. This is a pivot since it has 0 towards its left and in its beneath also. But notice that there's no pivot in this column. Why? A pivot cannot be 0, so these two are eliminated. And this is of course surrounded by 0 in its beneath, but it is not surrounded by 0 on its left because of this one, which means that due to this, the pivot is not there, which means that this column don't have a pivot, and the column which don't have a pivot but still it is satisfying this equation, then the variable of that column, in this it was x3, is a free variable. Free variable, I mean, you can substitute any value of x3 to solve this equation, right? The whole equation will be dependent upon x3, right? If you want to solve, I can show x1 plus x2 is equal to 4. Of course you have to do the calculation on your own, okay? And x2 plus, I mean, minus x3 is equal to negative 1, right? And the second one, the third one is 0 is equal to 0. It don't mean anything. And notice that we had assumed x3 is a free variable, okay? So let's assume x3 as alpha, right? Okay, so we get x2 is equal to negative 1, I mean simply alpha minus 1, and I'm going to substitute x1 over x2 over there. You get x1 is equal to 4 minus x2, which is equal to 4 minus alpha minus 1, which is equal to 5 minus alpha. So the whole equation is dependent upon alpha. And what is alpha? Alpha is simply x3, right? So that is why this is a free variable and rest all are dependent upon this. That is why it is called a free variable and these are called the dependent variables, okay? So let's see further. So now we are going to see the rank of a matrix. Let's see how we find it. Rank of a matrix. A matrix. So rank, suppose your matrix is A, is equal to the number of pivots. Suppose R. Basically number of pivots is represented by R, okay, in many cases. So this is how you find the rank of a matrix. But what's the need to find the rank? Let's see. So to check for inconsistency, for inconsistent system, the rank of A will not be equal to the rank of A augmented B matrix. And this is how you will check. You can check for inconsistent system, but of course we also know other methods also. We don't need to check for rank because you remember the previous example, right? But still this is also a method, okay? And for consistent unique solution system, the rank of A is equal to the rank of A augmented B matrix and is equal to n. Well, what is n? N is the number of variables, right? So the number of variables. Okay, I hope it is clear. And for consistent infinite solution system, the rank of A is still equal to the rank of A augmented B matrix, but in this case, suppose this is equal to k, the k is less than the number of variables. So in that case, you will get infinite solution. Okay. So this is how the rank helps us to determine the consistency of a system and the number of solutions, that will it have a infinite number of solutions or will it have unique solution, right? So this is another question, and in this also we need to solve for this augmented matrix. Well, let's see. I won't solve it on the board. If you want, I will just upload the solution. I'm right now just writing the answer, that what we are going to get. Since of course we have very less time, and if I devote the class time towards the calculation portion, you won't learn anything. I'm worried about to make you learn new things, not about the calculation part. This is just very simple thing which you can do on your own. Okay. So you get basically A augmented B 1 0 0 negative 1 2 to 0 1 4 0 beta. I guess it is beta plus 1. So on solving that augmented matrix, you are going to get this matrix, right? It is a very big matrix, of course, but you should know the basic method, that you have to create just zeros beneath these numbers, nothing else. And in the row, you have to try to make as many zeros as you can. Okay, this is the basic idea. So notice that if beta is equal to negative 1 is not equal to negative 1, in that case the system is inconsistent. Why? Because in this case it will be like 0 is equal to some non-zero quantity, which is not possible if beta is negative, if beta is not negative 1, right? So in this case it is inconsistent, right? And notice that if beta is equal to negative 1, in that case it is consistent, right? Okay, is it fine? It is consistent. But does it have infinite solution or finite? Well, we need to check. Okay. So how many pivots are there in this case? Well, this is a pivot. Of course, 2 is not a pivot because it is covered by, it is having zeros beneath it, but it is not having 0 towards its left. Similar is the case with this and all this number. Okay, 1 is a pivot in this case, 2 is a pivot, right? Okay. So we have 3 pivots in this case, and how many unknowns are there? There are 5 unknowns, which means that the rank of A is equal to 3, since the number of pivots is 3 in this case, and the rank of A augmented matrix B is also 3, right? Notice that when you substitute 0, it will become 0 in this case. So it also becomes a matrix with 3 pivots, right? You can see easily. You won't get any other pivot except these 3, right? So they are equal, but the number of variables is 5, which means that 3 is less than 5, which means that solution there are infinite solution in this case, right? Okay. And one thing to be noticed over here is that x1, x2, so x2 and x5 are free variables, right? Are free variables. Why? Because they don't have pivot. That is why they are free variables. So you can assume x2 as alpha 1 and x5 as alpha 2, and you can write all the variables x1, x3 and x4 in terms of alpha 1 and alpha 2, and you will get the solution, right? But there will be infinite solution which will depend upon the value of alpha 1 and alpha 2, right? So this is how you solve a linear equation which has infinite solution. You will find out the free variables and then write the dependent variables in terms of x2 and x5, right? You can of course do it. You have all the equations. You can just express x1, x3 and x4 in terms of alpha 1 and alpha 2, and then you'll get the solution, right? Infinite solutions. Okay. So with this we come to an end to the system of linear equation, and now we are going to start with field and vector spaces, right? So now let's start with fields, right? Okay, let me write the definition first of all, then we are going to see it further. So let F be a non-empty set which is closed, under two binary operations. I hope you know binary operations. If you don't know, you can check out my video of algebraic structures so that you can get a clarity. I can't discuss that right now because of lack of time, as the lecture will go very big. Binary operations, okay, denoted by, in most of the cases we will be only dealing with the plus and the multiplication sign. So that is why I'm going to represent it with plus and multiplication sign, right? Okay, then if this is a field, if for all a comma b comma c belonging to f, the following property holds. Let's see what are the properties. Well, there are many properties in this case, but don't worry. The first one is very simple, the commutative law. Commutative commutative law. A plus b is equal to b plus a, and this one, right? This is the first property. Then there's associative law. Of course, I'm not writing the associative law because you know this. I mean this associative law, the term I'm not writing. A this, okay, and this is equal to a, right, like this. And the distributive property holds in this case. Okay, is it fine? Okay. Fourth property, there exists 0 comma 1 belonging to f, satisfying what, a plus 0 is equal to 0 plus a is equal to a, and a operation 1 is equal to 1 operation a is equal to a, right? This is how you write it. And for any u belonging to f, there exists a negative a belonging to f such that a plus a inverse is equal to 0. Let's see the sixth property. For any a belonging to f, a is not equal to 0, there exists a inverse belonging to f such that a operation a inverse is equal to a inverse operation a is equal to 1, right? So these are the properties for a non-empty set to be called a field F, right? Under the operations plus and multiplication, addition, multiplication, right? So we will use this idea of field and we are going to apply it in the concept of vector space, right? So let's see that, and it is a really interesting topic, right? Okay. So now we are going to study vector space. Okay, let me write the definition and then we will discuss it. Okay, a vector space over a field F, and in most of the cases we will be assuming the field as a set of real numbers in this case, right? And okay, let me write the definition, then I will tell one thing. Is a set V of elements elements called vectors. Well, it is not the normal vectors. In this case, a matrix is also a vector, okay? So don't worry about that. It is just some terms which we are using, okay? A polynomial will also be a vector in this case. So don't worry about that. Together with two binary operations called vector addition and scalar multiplication. And I'm really not well, so that is why maybe I might sound a lot down than my other lectures, but still try to bear with me because I am also trying my best to record this lecture, but I wasn't in the condition to record this lecture. Still, I thought to record so that I can help. Okay, so please understand this. Okay, so scalar multiplication, if the following axioms hold. Okay, so what is a vector space? A vector space, we are operating over a field F, is a set V of elements called vectors together with two binary operations called vector addition, vector multiplication in the following axioms hold. Well, I hope you did not understand anything what I said. But still, let me tell the condition first of all, and then we will see it using example. Some examples actually, not just a one. So the first property which it should hold is that the closure property u plus v should belong to, suppose let me write it clearly, if u comma v belong to capital V, then it implies u plus v should also belong to v, right? For all u comma v, right? Okay. The second property, if lambda belongs to f, then and u belongs to v, then it implies that lambda times u should also belong to v. This is again the closure property, right? Okay. For all lambda. The third property, u plus v must be equal to v plus u for all u comma v belonging to capital V, right? The fourth property, u plus v plus w is equal to u plus v this associative property. U, v and w are the vectors of the set capital V, right? Okay. The fifth property, there exists this is a zero vector belonging to V. This is called a zero vector in vector space. Of course, a zero matrix, a null matrix is also called a zero vector in this case. So don't worry about the terms right now. Just understand the concept, nothing else. Okay. So such that a plus 0, I mean a plus the null matrix is equal to u. I mean, sorry, it should be u. Why I wrote a, I don't know. For all u belonging to capital V, right? Let me write the sixth property, and what it states: for each u belonging to V, there exists an inverse element belonging to additive inverse belonging to V, such that u plus this quantity must be equal to 0, right? The additive inverse. Let's see the next property. Well, don't worry that I'm telling so much properties, I mean the axioms. So how will you remember? I'm telling it, okay? Don't worry about it. So lambda times mu u is equal to lambda mu times u for all lambda mu belonging to f, and for all u belonging to v, right? This is another axiom, and let's see the eighth axiom. Lambda times u plus v must be equal to lambda u plus lambda v. Lambda belongs to, for all lambda belonging to the field f, and u comma v belonging to f, I mean vector v, vector space. And ninth property, lambda plus mu u is equal to lambda u plus mu u for all lambda comma v belonging towards to r, and u belonging towards not r, sorry, the field f, right? But in most of the cases we will be assuming the field as the real number, right? The set of real numbers. So that is why we could have written r over there, but since I've defined over here fields, that is why I'm writing f over here. Okay, so don't worry about this. Okay, now this is clear. And last property, for each u belonging to v, there exists one belonging to the field such that one operation u is equal to u. Okay, and this is the identity element, of course. Okay, so I told so many properties. So how we are going to remember this? Well, it depends. Of course, to check for a vector space, you only need the first and the second property. Just these two properties to check for a vector space, right? Do you understand this? Why? Because if you prove the closure properties, then all other properties are trivial, which means that they all are contained inside these two properties. So for any calculation, I am going to use only these two properties, but it depends on your exam that if they want you to prove all the properties, then you have to prove everything. But of course, in general, these two properties are enough to check for a vector space. You don't need to check for this because it will be automatically available after you prove this. And you can yourself check that if you prove these two properties, then these all are trivial. Even if you don't remember in the exam, you can still prove everything if you know these two properties. Okay, so these two are really important to check for the vector space. Okay, so let's see further. We will see some questions, right? I will try to cover some questions, but really I'm not well, so that is why I won't be able to cover much questions, but still I will try my best to provide you the best knowledge in less time so that you can do better, right? Okay, so let me erase this and I will be right back. So in this we have to check that Rn, is it a vector space over R, where R is the field, right? And what is Rn? Well, if I write the coordinate system a comma b, then it is R2, right? And if I write a, b and c, it is R3, right? Since it is formed by this cross product, right? Okay, And similarly for n system, I mean the n tuples, it is Rn, right? So this is how you write it. Okay, so I told this, but how we are going to check for vector space? Well, I said we need only two closure properties to prove this. Okay, it is very simple. Let's see. Suppose you have a vector space A1, I mean the Rn set as this. This one is your first set, I mean the element, you can say whatever. Okay, and this second till Bn belonging to Rn. So what was the closure property? U plus V should belong to the vector space, I mean the set V, right? So in this case, if you add them, you will get A1 plus B1, A2 plus B2, right, till An plus Bn, and it will be belonging to Rn. Why? Because A1 was also a vector and B1 was also a vector. So when you added it, you again got a vector only, right? And similar is the case with the other system, other coordinates, which means that your final result is also belonging to Rn, right? So that is why first property stands. Okay, now let's see the second one, that lambda times u must belong to V, where lambda belongs to, for all lambda belonging to F, in this case it is R, right? Okay, suppose you have x1 x2 till xn belonging to Rn, you multiply by x1, and like this, no, I mean with lambda you are multiplying this whole element. So when you multiply, you get lambda x1 lambda x2 till lambda xn, right? And it is belonging to Rn. Why? Because it is a scalar and is a vector, so the product is still a vector. That is why this whole expression is still belonging to Rn. So we proved these two properties, which means that Rn is a vector space over R, right? Don't go by my writing, of course. So it means that R2 is also a vector space, R3 is also a vector space over R, right? Remember this. Okay, so now let's see the next question. So we need to now check that is it a polynomial space or not. Again, it is just another way to say about vector space, so don't worry about it. Okay, let's see how we define this polynomial P and T. It can be written as like this. Suppose let me write it simply like this. Pt is equal to a naught plus a1t till suppose as ts, right, where s is less than or equal to n, since the maximum degree is n in this case, right? Okay, okay, so p1t ast p2t b naught b1t till bsts. I hope you're understanding. This is the first polynomial, this is the second polynomial, right? And now we're what going to do is we are going to add them, right, to check for the closure property. P1t plus P2t is equal to a naught plus b naught plus a1 plus b1t till as plus bs t to the power s. And notice that a naught plus b naught is a scalar, a1 plus b1 is a scalar, and so it means that this is also belonging to R, I mean the P and T, right? Okay, and the second property, suppose lambda belongs to R, for all lambda times suppose P1T, you can assume P2 also, you can assume anything, right? Suppose P of T, just a general term, C naught plus C1T till Cn or CSTS multiply by lambda, let lambda c naught plus lambda c1 t till plus lambda cs ts. Again lambda c naught is again a scalar, this is also scalar, this is also scalar, which means that it belongs to p and right, which means that this is a polynomial space over R, right? Is simple. Now we have to check the matrix space over R, right? Let's see. So M cross N can be written as A11 till AM1 till A1N till AMN, right? Okay. So this is your suppose first one, and the second one M cross N is equal to suppose B11 till B1N and so on till BM1 till BMN, right? And if you add it, you will get A11 plus B11 and like that. It will be the general term will be this, right? Of the whole matrix. Okay, maybe the representation is wrong, but still I want to just tell because I can't write everything due to my health right now, but still if you can understand and cooperate a bit. So if you add, you will get these type of expressions only, and which will belong to the matrix mm cross n only, right? And if you multiply by a lambda in this case also, then also it will be still belonging to m cross n. Why? Because lambda is a scalar and these are the vectors, so it will yield a vector only, right? This is how you check for the matrix space, right? Okay, let me see what next we are going to do now. Now we are going to do vector subspaces, right? Okay, so what is a vector subspace? Let's see that. Well, let V be a vector space and of course over F, and let W be a subset of V, right? Then W is a subspace of V if W is itself a vector space over F, right? Okay, with respect to same operations, right? As in V, right? Basically, if W is a subset of a vector space and that W is itself a vector space over F, then it is called a vector subspace. That variable, I mean the vector W, okay, the set W, I mean. So the criteria for vector subspace, well, let's see what are the criteria. Criteria for vector subspace. First one, U plus V should belong to W, and second lambda U should belong to W. U comma V belong to for all belonging to W and for all lambda belonging to F or the field, right? Just the similar condition, the same condition as in the case of the vector space, nothing else. Okay, so we have a question that U is equal to A comma B comma C such that A is equal to B is equal to C, and this U is a subset of R3. So we need to prove that this U is a vector subspace of R3 even. Okay, so let's see. So what are the conditions? Well, since A is equal to B is equal to C, which means you can assume the one vector as A comma A comma A, like this, belonging to U. You can assume B comma B comma B belonging to U. You add them, you get A plus B, A plus B, A plus B, which is again belong to you. What did I just did? Okay, I assumed a variable A first, and since A is equal to B is equal to C, which means that I choose any variable, it will still be equal to a single variable, that is a in this case, and in this case it will be equal to b. I mean all the three coordinates are same, right? So this is the first vector, this is the second vector. I added both the vectors. The closure property u plus v belonging to u, I mean u, right? This is your u, this is your v, and u comma v belongs to u, right? Okay. So now notice that this and this all have the same value, just like the condition, which means that this itself belongs to u, right? Okay, first is checked. Now let's multiply by lambda a belonging to, and this will be equal to, of course you need to know that what statements you have to write, of course, that lambda belongs to the field or r, right, like that, and then you need to solve. I am not writing everything because I'm not well. Please cooperate with me. Okay, so you just multiply, you get lambda a belonging to u again. Why? Because all the variables, all the elements are same as per the given condition, which means that u is a vector subspace of r cube, I mean r3. Okay, so now let's coming to the linear combination of vectors. Let's see what is it. So now coming towards the linear combination of vectors, well, let's see. An expression of type lambda1 v1 plus lambda2 v2 till lambda n vn, such that lambda I mean lambda1 lambda2 everything belongs to real number, is called linear combination. I'm not writing everything, of vectors v1 till vn belonging to, suppose, some vector space v. Okay, so don't worry about that term, you don't even need to write that. Okay, so basically if the vectors v1 till vn can be expressed as a linear combination like this, then this thing is called linear combination of vectors. Okay, let's see with the help of an example, right? Okay, so suppose the question states, let alpha is equal to 435 transpose and beta is equal to 013 transpose, gamma is equal to 211 transpose, and delta is equal to 422, right? Okay, so express alpha as linear combination of the vectors b comma, I mean beta comma gamma. And for your practice you can do this question, beta as linear combination of gamma and delta, right? So we will be doing this one, and this is your homework for your understanding purpose. Okay, solution. Well, alpha is basically equal to 435, beta is equal to 013, I mean it's transpose, so it will look like this, 013, and gamma looks like this, right, since it is a transpose. So to express alpha as the linear combination of beta and gamma, we need to write alpha as lambda 1 beta plus lambda 2 gamma, right? And we need to solve for lambda 1 and lambda 2. Let's solve it and let's see what we get. So now let's express alpha in terms of beta and gamma, I mean as the linear combination of beta and gamma. So what was alpha? Alpha is 435. 435 is equal to lambda 1 times, what is the value of beta? 013 plus lambda 2 times 211. You can solve 435 is equal to 2 lambda 2 and lambda 1 plus lambda 2, and this is 3 lambda 1 plus lambda 2. You can solve this equation very easily. What you will get is that lambda 2 is equal to 2 and lambda 1, how? Well, it is very simple. Still I'm telling, 4 is equal to 2 lambda 2, which means lambda 2 is equal to 2, right? And lambda 1 plus lambda 2 is equal to 3, which means lambda 1 will be equal to 3 minus lambda 2, and lambda 2 is 2, so we get lambda 1 is equal to 1, right? And this is the value. But still our job is not done. We need to check in the third equation also, because there's a possibility that these two roots or the solution for lambda 1 and lambda 2 may not satisfy this equation. If it does satisfy the equation, then alpha can be expressed as the linear combination of beta and gamma, and if it don't satisfy this equation, then in that case it can't be expressed as the linear combination of beta and gamma, right? This is how you check. So 5 is equal to 3 lambda 1 plus lambda 2. Let's substitute the value. 3 into 1 plus 2. Yeah, 5 is equal to 5, which means that alpha can be expressed as linear combination. LC means linear combination for my simplicity, okay? Try to understand it as the linear combination of beta and gamma, right? Given by lambda 1 is this, lambda 1 beta plus lambda 2 gamma, which implies alpha is equal to 1 times, I mean, beta plus 2 gamma, right? Like this. But suppose if it was a 6 over here instead of 5, then if you would solve, you will get 5, which is not equal, since 3 into 1 plus 2 was 5, and since 5 is not equal to 6, in that case we cannot express alpha as the linear combination of beta and gamma. So this is how you check for the linear combination of vectors, right? Okay, now let's see linear dependency, I mean the linear independent vectors and linearly independent variables. So let's see what do we mean by linear independence of vectors. Let's see. Suppose let V be a vector space, right? Of course, we are dealing with vectors, so we will need vector space, of course. A finite set of vectors v1, v2 till vn of capital V, this is capital V, is said to be linearly independent if till lambda and vn is equal to 0, implies lambda 1 is equal to lambda 2 is equal to lambda is equal to 0. Only then it is called linearly independent, right? The vectors then only will be called linearly independent if lambda 1 is equal to lambda 2 is equal to lambda n is equal to 0 for this linear combination, right? I've been understanding this, and we will understand it with respect to a question also. And of course, lambda I is a scalar, right? And vi is vectors, of course, simple, right? Let's understand it using a question also, and then we will move further to vector span, right? Don't worry about these terms, I mean not the vector span, sorry, linear span, okay? Don't worry about these fancy terms, they are just terms, right? Only, nothing else. They are very, very simple. It is very simple topic actually, if you try to understand it with pure dedication, because it is simply the vector space and everything. It is very simple. If you know the method, you can do the problems. And of course, I never teach for marks or anything like that. I teach for knowledge, because that is my passion. That is why I don't care that we practice many problems or not, but I try to make sure that you understand every concept. Just if you are done with the concepts, you don't need to practice much. You can apply them directly, right? Of course, you need some practice, but not that much to like rote learn the questions. No, you don't need to do that. You just need to understand the concepts, nothing else. That is the beauty of mathematics, nothing else, right? Because if you understood the concept, you can do anything in mathematics. But if you are just learning the questions for sake of marks, then mathematics is really tough. But if you love mathematics like anything, you are loving the concepts of mathematics, then you will be very much great in mathematics. Very much. I can guarantee that. Maths is not a subject, it is a part of life. Remember that. So this is a question that we have to check the linear independence of these vectors. So how we will check? Well, suppose V belongs to, we need to check for lambda 1 V1 and lambda 2 V2, lambda 3 V3 is equal to the 0, right? Of course it should be a 0 matrix, but for now just understand it. So lambda 1 times 1 negative 1 0 plus lambda 2 times 0 1 negative 1 plus lambda 3 times 0 comma 0 comma 1 is equal to 0 comma 0 comma 0, basically the null vector. Okay, so you get lambda 1 plus 0 times lambda 2, just add the components, right? Like you do, you add the x component, y component, z component. Similar is the case over here also. Plus lambda 0 lambda 3, right? Okay, comma lambda 1 negative lambda 1 plus lambda 2 plus 0 lambda 3, right? Are you understanding what I am doing? Wait. And then this 0 lambda 1 plus negative lambda 2 plus lambda 3 must be equal to 0 comma 0 comma 0. Well, what did I done just now? Let me explain it. I hope that you must be having confusion. You multiply lambda 1 with these elements, you get this negative lambda 1 0 plus lambda 2, you get over here 0 comma lambda 2 comma negative lambda 2 plus 0 comma 0 comma lambda 3. Now add them. Add, right, the components you are going to add, and you're going to get this, right? That is what I did in a one step. Lambda 1 comma negative lambda 1 plus 2 comma negative lambda 2 plus lambda 3 is equal to 0 comma 0 comma 0. So from this you can just match the coordinates. You get lambda 1 is equal to 0, and you get lambda 2 is equal to lambda 1 only, which is equal to 0, and lambda 3 is equal to again lambda 2, which is equal to 0, which means that lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to 0, which means that the given vectors are linearly independent, right? Okay, now let's see a question in which the vectors will be linearly dependent instead of being independent. Let's see that question. Okay, so these are the given vectors and we have to check for the linear independence in this case. Let's see. Okay, lambda 1 v1 plus lambda 2 v2, it must be equal to 0, right? Simple condition. Lambda 1 0 comma 0 plus lambda 2 1 comma 2 is equal to 0, which means that lambda 1 will get vanish actually, plus lambda 2 comma lambda 2 is equal to 0, which means that lambda 2 comma 2 lambda 2 is equal to 0 comma 0 0 comma 0 0 comma 0, of course, which means lambda 2 is equal to 0, but lambda 1 belongs to real number, which means that lambda can take any value, which means that it is not necessary for lambda to take only 0. It can take many values, any value it can take. It means that it is linearly dependent, right? Not independent, because we're not getting the unique value of lambda 1 as 0. We are getting infinite values. Even if we would have get 0 also, 0 comma 1, just two values, still it was independent because there was 1. Lambda has to be 0. Lambda I has to be 0 for being linearly independent. All lambda should be 0. I'm repeating again and again. Just remember this thing, okay? So with this, we are coming to linear span now, okay? So let's start with the linear span, and it is simple concept. You need to just practice and understand the concept, nothing else, okay? So don't worry about it. Let's come to linear span now. So what is a linear span? Let me define it, okay? Linear span of vectors v1 v2 till vn is defined as span v1 v2 till vn is equal to the summation I goes from 1 to n of lambda I vi such that lambda I belongs to R. Well, it is just the linear combination, nothing else, right? Nothing else. Very simple. So basically it is the collection of all vector combinations of v1 comma v2 till vn, okay? The collection of all the vectors is called the linear span of vectors v1 comma v2 till vn, right? This is how you define the linear span, okay? Very simple, very simple. It is just the linear combination, nothing else. And the name suggests that what is it? It is like what is it? But it is very simple, right? It was just linear combination, nothing else, okay? So let's see a question to understand it better, okay? So this is the question, that is the vector, this vector, in the span of the vectors this and this. Of course, notice you have a transpose, okay? Solution. So basically if we assume okay, span v1 comma v2, it must be lambda 1 v1 plus lambda 2 v2. In this case v1 is equal to this matrix and v2 is equal to this matrix, right? Or this vector, right? And as per the question, it must be equal to this vector, right? This suppose v, right? For simplicity, okay? So what we are going to get is that lambda 1 times 4 to 7. Notice that it is a transpose sign, so that is why I transposed it. Plus lambda 2 times 314 is equal to 100. Notice the transpose sign, it is really important. You can't miss that, okay? You will lose marks in the exam also, and conceptually also it is not good, because you should know the definition of transpose, right? Okay, so very simple. Lambda 1, 4 lambda 1 plus 3 lambda 2, 2 lambda 1 plus lambda 2, 7 lambda 1 plus 4 lambda 2 is equal to 100, right? Very simple. So you get 4 lambda 1 plus 3 lambda 2 is equal to 1, 2 lambda 1 plus lambda 2 is equal to 0, 7 lambda 1 plus 4 lambda 2 is equal to 0, and let's solve these two equations to get the value. What we are going to get is that well, first of all, solve this. Lambda 2 is equal to negative 2 lambda 1. You substitute it over here. Here 4 times lambda 1 plus 3 times, what is lambda 2? It is negative of 2 lambda 1. It should be equal to 1. So we have 4 lambda 1 minus 6 lambda 1 is equal to 1. So we get lambda 1 is equal to negative 1 by 2. Right, I hope it is not too much inclined. You understand? Lambda 1 is equal to negative 1 by 2, which means that lambda 2 is equal to negative 2 times negative 1 by 2, which is equal to 1, right? So we get the value of lambda 2 as 1 and lambda 1 as negative 1 by 2. Is it satisfying this equation? Let's see. 7 times what is lambda 1? Lambda 1 is simply equal to negative 1 by 2 plus 4 times 1. Of course, it is not equal to 0, which means that this given vector is not a linear span, or just is not a span of is not in the span of given vectors. Okay, this is how you check for the span. Basically it is just the checking of linear combination, nothing else. Okay, now let's move to the next concept, something called spanning set. Okay, let's see what is it. So let's see what is a spanning set. Suppose the set this v1 comma v2 till vn is said to form a spanning set of a vector space if for any v belonging to capital V, this is a vector and this is the vector space, scalars alpha 1 alpha 2 till alpha n belonging to R, such that V, this element or this vector, can be expressed as this sum, right? Alpha I V I. Well, we will understand it using a question, right? No need to worry. So we need to check that whether these vector form a spanning set of R3 or not. Let's see, right? It is simple. So suppose a V belongs to capital V, and of course these also belong to the vector space only. So, and over here what is V? V is basically R cube in this case, right? So we can express V as V1 alpha 1 plus V2 alpha 2 plus V3, I mean not this, sorry, some lambda 1, the constant, the scalar, multiplied by the vector, given vector, suppose x1 plus lambda 2 x2 plus lambda 3 x3, right? So what is V? We can assume the V as a general vector v1 v2 v3, right? It is the vector, of course, since it is R3, so there has to be 3 elements, right? So basically it is v1 v2 v3 lambda 1 times 1 0 0, this is your first vector, plus lambda 2 lambda 3 0 0 1. We solve it. v1 v2 v3 lambda 1 lambda 2 lambda 3. Solve this much at least, right? Very simple equation, right? So we get lambda 1 is equal to v1, lambda 2 is equal to v3, I mean sorry v2, and lambda 3 is equal to v3, which implies that v can be expressed as v1 times 100 plus v2 times 001 plus v3 times 001, which means that these vectors form a spanning set of R3. I hope you're understanding that how we got this. Okay, and of course V was v1 v2 v3. Okay, this is how you express, you just substitute the value of the lambda. Okay, very simple, right? It is very simple, right? Okay, So, and there might be a condition when you don't get unique value of lambda, or you get that there exists no lambda. In that case, it is not forming a spanning set, right? Of course. And there's a chance that you get unique value of lambda 1 and lambda and so on, like you got in this, or you might get free variables. In that case also spanning set is formed, but there's not uniqueness in that, like in this case, because here it is only a single solution. In that case it can be infinite. And if no lambda exists, maybe suppose lambda 2 and lambda 3, lambda 1, lambda 2, lambda 3, in that case suppose lambda 2 don't exist, even lambda 2 don't even exist, in that case there will be no spanning set. But if suppose lambda 2 is a free variable, then spanning set exists. Okay, we will see it later in the basis of a vector space, just a few minutes. So what is basis of a vector space? Let's see. Well, basis of vector space, basis is a linearly independent set that span a vector space V, right? Okay, so basis should be linearly independent set that span a vector space V, and we don't understand anything what it means. I know, but it's still wait for a few minutes so that I can explain it using a question, right? So there's one more definition I need to tell, and then we will understand it using questions. So don't worry about that. Okay. So number of elements in a basis is called the, I have the ink is over, so I have to refill it. The dimension is called the dimension of the vector space V, right? Okay, don't worry, we are just going to see this using a question, and let me refill my marker also. So in this case we have to check the vector space Rn, I mean the basis for the vector space Rn. Let's see, suppose you have E1 is equal to 1 0 0 0 and so on 0 transpose, E2 is 0 1 0 till 0 transpose, and so on till En is equal to 0 0 till 1, and I mean the transpose. Okay, so in this case, okay, why did I assume this? Because it is very basic thing which we will understand in some time. Okay, so notice that these vectors are linearly independent. Of course you can check they are linearly independent, because okay, lambda e1 plus lambda e2 till lambda n into lambda, I mean en, it should be equal to the zero matrix. And if you solve, you get the unique value of lambda 1, lambda 2 till lambda n as 0 only. That is why these are linearly independent, which means e1 comma en, they are linearly independent. So the first condition of basis is satisfied, that it should be linearly independent set, right? And this is linearly independent, right? Okay, and the second thing was checking for the span of a vector space, right? So suppose the vector can be written as Vn, right? You remember how to find the span? It is like that, lambda 1 times 1 0 0 till this, and so on till lambda n times 0 0 till 1, lambda n times 0 0 and so on till 1, right? Like this. Okay, solve, you get lambda 1 is equal to Vn and so on and so forth, which means that this vector, suppose V, this whole vector can be expressed as lambda 1 e1 till lambda n en. And what is the value of lambda? It is this, right? So you get V is equal to V1 e1 till V2 I mean Vn en, which means that it is also a span also, and it is linearly independent also. which means that this set of elements is forming the basis for Rn, right? Which means that, and yeah, to find the dimension. Dimension was the number of elements in the set of bases. In the bases, the number of elements for bases, right? So notice that it is E1, E2 till En, which means how many elements? N elements. The dimension is n of this vector of this basis. Okay. So let's see if we have some more questions. If we have, we will solve them, and if we don't, then we can end the lecture. Well, let's see. So we have to check the basis for vector space of all 2 cross 3 matrix, and of course it can be of any dimension. I mean of any number of rows and columns, but for simplicity I've assumed 2 cross 3. You can assume any matrix, you can assume m cross n also in a general sense, and you can solve, right? So in this case, the first uh, element we can assume 1 0 0 0 0 0. Why we are assuming like this? Because we know that all this will be linearly independent, right? 0 e3, okay, e4, 0 0 0 1 0 0, so until, of course I did not wrote e5. You know how to write it, that 0 0 1, right? So this is your basis vector. I mean, we don't know it is basis or not, but still they are linearly independent. How? You check lambda 1 plus lambda 2 into e2 and so on and so forth. You set it equal to 0, you will find that lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, lambda 6 are 0. So that is why it is linearly independent. First condition is checked. Now we have to check for the span, right? So suppose your matrix is A, B, C, D, E, F, right? So it has to be expressed as lambda 1 times E1 and so on till lambda 6 into E6. You need to solve for lambda now. 1 0 0 0 0 1 till lambda 6 into 0 0 0 0 0 1. You get the value of lambda 1 as A, lambda 2 as B, and so on till lambda 6 is equal to F. So basically you expressed this matrix in terms of A times 1 0 0 0 0 0 till F times 0 0 0 0 0 1, right? Okay, which means that this matrix, suppose if I represent it using M, is equal to AE1 till FE6, which means that E1, E2, E3, E4, E5 and E6 are the elements of the basis, and we prove that these are the basis of 2 cross 3 matrix. And what is its dimension? Dimension is simply equal to what? 6, or 2 cross 3, which gives 6, because we have 6 elements in the basis, right? Simple, very simple, right? And with this we come to an end to our lecture of linear algebra, and I hope that you understood a lot from this lecture, and maybe you enjoyed this video. Then please do like and subscribe my channel. And I'm really sorry, because of my health I might sound very much different than my other videos and not that much energetic. Still, I thought to make the video so that I can help. And if you enjoyed this video, please do like and subscribe my channel. Bye bye, take care.